the name of Almighty God, I am Master Asankosha, and today I want to talk about theory for electrophoretic transport interface. The electrophoretic transport interface models transfer of charged and uncharged species, and in addition sets up a charge balance equation for the electrolytic potential. The species concentrations are denoted Ci based on the SI is molar per cubic meter, and the potential Pl based on the SI is volts. The species are transported by diffusion, migration, and optionally convection according to the Nernst-Planck set of equations. The total flux of a species I is denoted Ni based on the SI unit molar per square meter second according to the equation 3-117, where Di based on the SI unit square meter per second is the diffusion coefficient, Zi is the corresponding charge dimensionless, and UMI based on the SI unit is S molar per kilogram, the mobility, and U based on the SI unit is meter per second. The velocity vector GI denotes the molar flux relative to the convective transport based on the SI unit is molar per square meter second. For detailed description of the theory of these equations and the different boundary conditions, see the transfer of diluted species interface. Now I want to go through the charge balance equation. The current vector IL based on the SI unit ampere per square meter is defined as IL is equal to sigma. Lower boundary is I, Z I, and I, where the summation is made overall species in the electrolyte. The governing equation for the electric potential is as follows, where QL based on the SI unit is ampere per cubic meter is the electric current source stemming from, for example, porous electrode reactions. For non-porous electrode domains, this source term is usually zero. Proton and hydroxide concentrations and electroneutrality section. Assuming that the total number of species to be n plus 2, the assumption of electroneutrality is sigma, the lower boundary is I is equal to 1, and the upper boundary is n plus 2. We have a ZICI is equal to 0. In water-based systems, the species positive hydrogen and negative OH are always present. The auto-ionization reaction for water is H2O, has a bidirectional with positive hydrogen and negative OH. This reaction is fast following the equilibrium relation as follows, where K omega is almost equal to 10 to the power of minus 14. Now the electroneutrality condition including the additional species positive hydrogen and negative OH reads as follows. Combining these two equations results in the following algebraic expressions for the concentrations of positive hydrogen and negative OH as follows. Mass balance equations for dissociation species assume a set of species psi describing co-dissociation steps from these equations, where Z0 is the charge balance of species S0 which has no dissociable protons, and chi alpha J is the acid equilibrium constant of the J dissociation reaction. The brackets here represents the species activity. The charge of each species is always deductible from the index I according to Z0 plus I and will be dropped from now on. If the proton activity is known, any species SM may be expressed using any other species cell according to follow. Setting M is equal to I and denoting the flux of species I by Ni using equation 3-117, the mass balance equation for the concentration CIR, which is subspecies I in the dissociation chain, is as follows, where R equilibrium Ij is the reaction source stemming from the J dissociation step, which R equilibrium I and chi plus 1 is equal to 0, and Ri any additional reaction sources. The reaction source contributions from the dissociation steps are generally not known but may be cancelled by checking the sum of all mass balance equations resulting in follow. Now I want to go through the average ionization formulation for large molecules. Large protein molecules are typically subject to a large number of dissociation steps as an alternative way to a long chain of dissociation steps. For describing protein transport, you can instead formulate the protein's transport based on the average number of protons removed from the molecule. A vaprin is typically provided as a function of pH. Based on experimental data, the average charge of a species then is equal to Z is equal to Z0 minus Vp, so that the flux of the species is written as equation 3-133, and similarly addition to the charge neutrality condition is ZSCI. When considering the condition to the current and charge balance equation, you need to take into account that the square average charge Z to the power of 2 is equal to Z0 minus V to the power of 2 is not equal to the average square charge. The addition to the current density vector is as follows. The average number of protons removed from the proton typically depends on the pH. If the average number of removed protons depends only on pH, the average square number of protons removed can be written as follow. And from this you can derive the average square charge according to this formulation. Now I want to go through the diffusivity mobility relations. The Stokes radius R of a molecule is related to the diffusivity according to the R is equal to K T divided by 6 P micro D, where is the micro is based on the SI is Pascal second, the dynamic viscosity, and K is a Boltzmann constant. For small molecules, there is a frequently and Nernst-Einstein relation between the diffusivity and the mobility. Um is equal to D divided by RT. For larger molecules such as proteins, the mobility may instead be calculated based on the Debye-Huckel-Henry expression based on the second reference according to the follow, where K1 divided by M is the Debye parameter, which depends on the ionic strength of the solution is defined for the ideal solution as follow, where epsilon is the dielectric constant of the fluid and epsilon 0 the permittivity of free space. Z to the power of 2 should be used if available in the formula above when calculating the ionic strength. The functional f above is based on the sigmoidal function, so that it ranges from 1 for car is equal to 0 to 1.5 for car has a tendency to the infinitely. Note that the Debye-Huckel-Henry expression approaches the Nernst-Einstein mobility as R tends to 0 for larger molecules, macroions, where the distance between the charges is large compared to 1 divided by K. The Linder-Storm-Lang approximation postulates a smaller contribution of two ionic strength, so that the Z-valent ion behaves as a monovalent ion with a Z-fold concentration. For an ensemble of n m smaller molecules and m macroions, the Debye parameter then is defined as follows. I read the literature for you was written by Musher and Saville and Torman. The name is the dynamic of electrophoresis, and the next one also was written by Moshe and Gebauer and Gasselwaska and Torman, and the name was Computer Simulation and Experimental Validation of Electrophoretic Behavior of Protein. Thank you so much for watching my tutorial video until the end. Today is 19th of May 2026, time is 12:15 p.m. Also, you can download the proper, appropriate, and related quantum multiphysics simulation file from my github.com/masterscript.